Taking the nitrogen cycle a little bit further, we'll look at more details, starting with the spatial patterns of N2O production. You want to look at the climate impact on N2O production and N2O feedback to climate, and whether the feedbacks can be constrained by observations. Again, lots of difficulties. N2O, as you remember, is a trace gas in the order of parts per billion. And compared to methane, which is also parts per billion, nitrous oxide is one order of magnitude smaller than methane, but it has long residence time, so it does, and it's got massive global warming potential compared to carbon dioxide of a couple of hundred, which is bad news, right? Just looking at the spatial patterns of N2O emissions from natural ecosystems for this period of 1990 to 2000. It's not very easy to get data. As you remember, even in the ice cores, nitrous oxide is not very well preserved. So this is in kilograms nitrogen per hectare per year. So the numbers are relatively small, but you can see the Amazonia shows up, the agricultural belt of the US, for whatever reason, this region of Burma and Thailand and the maritime continent show up, Western Ghats. So these are natural emissions, so obviously have to do with vegetation. So there is vegetation here, Sahel, of course, there is forests here, and Amazonia. Okay, so what do we do with that? Obviously we need to have some sense of how the natural ecosystem and other sources of nitrous oxide, natural sources, are going to be affected by climate, as well as how nitrous oxide itself feeds back to the climate, right? Ocean also produces nitrous oxide emissions, and you can see this paper from Zamora and Andreas Oschlies is looking at global marine nitrous oxide emissions in teragrams nitrogen per year from various studies, and it's their study here, and they use various scenarios of doing their simulations. And you can see that these are data interpolation based estimates, and these are model based estimates, and the uncertainty in them is fairly large. Okay, that's something to remember, and that they are they differ by a significant amount. So considering that the nitrous oxide has a high global warming potential, obviously we don't have a incredibly strong constraint on marine nitrous oxide emissions, and then we have to also see what that means for climate feedbacks from nitrous oxide. Overall, you need to understand marine and terrestrial ecosystem nitrogen cycles. Obviously, nitrogen fixing bacteria are critical, legumes, peas and so on, which are often used as cover crops to enhance nitrogen content of the soil. There are heterotrophs and other decomposers which are going to convert plant matter into nitrogen emissions as well, directly or indirectly, and it can be aerobic, anaerobic bacteria and fungi, and they produce ammonium, which then is nitrified into nitrites and nitrates. So there are nitrifying bacteria, and there are nitrogen fixing soil bacteria as well, as we mentioned for the ocean. So as vegetation is assimilating nitrate, it has this ammonium as an intermediate step in the ocean. In fact, nitrate is converted to ammonium most of the times to be used as a nutrient for photosynthesis. So these processes are critical. Why do I mention them? Because each of these bacterial functions, especially those that form nitrogen fixing bacteria that produce ammonium, they are very temperature dependent. So if you want to think about nitrogen cycle and its impact on climate and climate impact on nitrogen and nitrous oxide production, you have to remember that these mediating living things are very critical for providing nutrients. These we tend to call preformed nutrients, going from dinitrogen to the form that plants can use through the roots and so on. The details needed to understand the impact of temperature on soil moisture, soil carbon, soil nitrogen, and then denitrifying bacteria and so on. It's not easy, especially even in the ocean. You have regions where there are standard low oxygen regions where there are nitrifying, denitrifying bacteria and so on in the ocean, which also matter. So you have dinitrogen exchange with the ocean and flux in and flux out. Nitrogen fixation by the diazotrophs ends up producing ammonium just like on land, which is then converted by sedimentation and mixing. So you are thinking of the euphotic zone here where there is enough light for photosynthesis, euphotic zone, and the darker part of the ocean, a lot of the chemical reactions and reforming of organic matter into nutrients and so on happens. The nitrification from ammonium into nitrite and nitrate, or denitrification, as we mentioned before, from nitrate to dinitrogen, are all dependent on temperature. Okay, so and the phytoplankton species, some can easily take up ammonium, and some take up nitrate and convert internally as needed. So you can imagine again the difficulty of representing these chain of links if you want to worry about nitrogen cycling in the ocean. This is why you get these sorts of uncertainties. It depends on the details in which these processes are represented in the model. They're not simple, especially because to constrain them with data is not so easy either. You can measure primary production and so on from satellites or other methods, but to actually measure these rates in an open ocean environment is all but impossible. And if you do that in the lab, then you have to understand how what that means actually in the real world and so on. So given all that, if you look at the distribution of nitrate in the ocean at the surface at 10 meters in micromoles per liter, we talked about regions where nitrate is high. So if you remember, this is the upwelling region where primary production is high, but nitrate is still relatively high compared to the ocean deserts. Remember, Hadley cell sinks and you get deserts on land approximately at those latitudes, but in the ocean you get trade winds and westerlies which create converging waters in the subtropical gyre, which pushes the water down, so there is no nutrients at the surface, so you get deserts. So why is there production as well as unused nutrient, nitrate? As we mentioned before, these are called HNLC, or high nitrate low chlorophyll regions, because iron is a limiting nutrient here. There are also iron limiting situations here, and there are maybe phosphorus limiting and iron limitation and so on happening in other places. But you get a sense of how the surface nitrate distribution looks. You can see the Indian Ocean only has high nitrate over here in the upwelling Somali region. But if you go to depth at 1000 meters, there's plenty of nitrate everywhere, except for these deep water formation sites where you're bringing lower nutrients to depths, so you have less nutrients here. Remember the profile. Surface nutrients are low because they are used up for photosynthesis, and they are accumulating in the deeper ocean because they are reformed. So since this is newer water sinking, you see that generally there is low concentrations here, whereas this water is old and it keeps accumulating nitrate over time. So relatively high, almost double the values here overall. And you can see the Southern Ocean exchange produces this great hemispheric asymmetry in both the Indian Ocean and the Pacific Ocean in terms of nitrate distributions. All these things have to be considered as opposed to the nitrogen fixing on land either by legumes or bacteria. In the ocean we have diazotropes, so you have to again look at the nitrogen to phosphorus ratios and their relation to denitrification as well as nitrogen fixation. Why? There is a relation between low N2P and nitrogen fixation to some extent, but we also need to know how the ocean nitrogen cycle, nitrogen fixation by diazotropes and so on are going to be affected by global warming. The first order effect is the ocean surface warms, so the gradient increases, so the stratification is what we call the gradient, makes it harder to mix the high nutrients below the surface into the euphotic zone where photosynthesis happens. So all these processes are going to have an impact on how nitrogen is going to be cycled, and then that also determines how the carbon and nitrogen cycles will interact. This is just showing some idea for the future how the sensitivity of regional nitrous oxide emissions to air temperatures and water-filled pore spaces in the soils are going to behave. So this is showing in regions with snowmelt, growing annual water-filled pore spaces of various percentages and so on. And the observed data seems to show that there is a trend that is significant in terms of the nitrogen emissions in gigagrams nitrous oxide nitrogen per year. Okay, that's kind of a unit that is used to connect nitrous oxide to nitrogen. But that's the main story, that nitrogen cycle has an impact on the climate through nitrous oxide, which is a strong global warming gas. The feedback from climate to nitrogen occurs through all these processes of nitrogen fixation and microbial activity and so on. And the feedback is not as well constrained as we would like from data, and the models have some uncertainty, but they are obviously getting better. Okay. Don't think everything is bad news. It's important to understand what the uncertainties are and how well we know the processes. Once you know those, modeling becomes easier. Even deciding which data is important to constrain the models and validate the models becomes easier once you understand the processes and these cascades of feedbacks and interactions.